All right, so welcome to the course. This is Mechatronics. And I think a course with this name requires a little bit of introduction. Classically, and from my experience, often courses like this, especially when they're semester long or 2 semester long or 3 semester long, they often devote entire lecture just to introducing basic ideas. We're not going to do that. We are going to be a little bit faster, but let us do a little bit of introduction. So first of all, this is the type of picture you would see if you Google mechatronics, just the word. This is a very popular picture. You would see it pasted on the walls of universities. People love to dwell on it. It's very popular. I mean, probably because people like diagrams in general. What this picture is supposed to tell you is that mechatronics is like intersection of everything good, right? You have like pretty much everything you study: computers, control systems, electronics, mechanics, and all of this is somehow combined to produce mechatronics. Great. Let's try to be a little bit more clear. So originally, mechatronics was thought of as a combination of two words, mechanics and electronics. So that's why mechatronics, mechanics, electronics. The idea, the reason why this became a thing was because people started to realize that it is possible to produce better products if you simultaneously design the electrical and mechanical parts. So rather than doing mechanical design, electrical design, then fitting them together somehow, you can do it simultaneously. And what you get is what we call synergy. So synergetic design, where the sum is somehow more than its parts. Like the whole is more than the sum of the parts. Synergetic design. We call it synergistic, I think sometimes synergetic. All right. So that was the idea. That is second half of the previous century. So quite a while ago. Now we don't do just mechanical and electrical design. We also add sensors and code and, of course, control theory and everything else. So the amount of stuff that we combine clearly increased. And you can argue that it was always on the table. But the word mechatronics is descriptive and good enough for the purposes. All right. So it is about design. That is what I want to stress. Okay. Now, this idea of design, why is it good? Why is it good? Let's first answer this question. Why is it good? Well, it is good because you can imagine sometimes during design process, you may optimize mechanical design in terms of weight, in terms of durability, in terms of friction, other mechanical performance metrics, and you would leave no space for no space for meaningful sensors, for example. Not even you don't leave any space. You don't even think of sensors as part of your design process. You just design mechanical thing, and then someone else has to add sensors on top. That is not optimal. Like you could just introduce sensors during the design process, during the mechanical design process, find perfect space for them. You would have more constraints during mechanical design, but it would be good, right? Or you could say, okay, while you do mechanical design, you think about how the object will be controlled, right? What does it need for control? Like it needs sensors, for sure. Also, it needs some sort of electrical circuit that would control it. It needs to dissipate heat, which will be produced by electrical circuit. and by electricity involved in general. Like we will discuss it in this lecture where the heat comes from. So you need to dissipate heat. Maybe you need to protect your circuits from various types of electromagnetic fields that are produced elsewhere. You can also think about other effects like moisture, etc. And also importantly, if you know how your how your motor will be controlled, you can think about like in particular like how electrically it would look like the control of the motor. You can think about the dimensions of the boards. You can find the way to fit them in very nicely and neatly. You can optimize the wiring. You can make everything more compact and so on. It sounds very good. Sounds very good, and it is. Like I mentioned, the difference of buying a motor, buying a sensor, buying a driver, what we call driver scheme, buying a controller, and now trying to fit all of this together and designing, let's say, some sort of mechanical contraption that connects the shaft of the motor with the sensor, for example. All right, all of this sounds like a pain, and compare this to just buying a motor that has all of this inside. Okay, big difference, big difference. Now, this sounds very nice, and it is very nice, but it is not the only way to design things. That is an important point to think about. Like, mechatronics is beneficial because it provides better performance, for example. But producing things independently provides economic benefit. Like if you can produce 100 mechatronic modules a year, they would cost quite a bit. And if you can produce individual components by the volume of 100,000 a year, they would cost much less. It's called, what do you call it? Economy of scale. Economy of scale. The benefits of like economic benefits are significant. In some areas, like airspace, economic benefits are not as important as high performance. In medical robotics, it is not as important, and so on. But in retail, in various types of simple automation, in some primitive, like more simple applications of research, where you do just like first steps in some direction, etc. High performance is not necessary. What you need is accessibility. What you need is something being cheap. So just as an example, like we can point out Atlas by Boston Dynamics, the robots that can dance, do somersaults, etc. This robot has tons of highly optimized mechatronic modules. It has its legs are designed basically with the hydraulic components in mind, like the valves, just the ways the liquid goes in and out, etc. is all optimized, and it's all kind of designed to make as little weight as possible, and with sufficient performance in terms of durability and everything else. Also, it is optimized for repairs, etc. Like it's very good. It's very good design, but it is all this design is only for one robot, right? So the robot costs incredible sums of money to produce, and no one sells it. On the other hand, A1, I'm using one of the names of this robot. The robot goes through various iterations. The quadruped, produced by Unitree, company from China. The robot is everywhere now. You can find it on almost every part of the globe because it is very cheap. And it uses off-the-shelf components, motors, various types of electronics. Like some of it is, how should I put it? It's not something you can buy in a grocery store, but it is not a rare. Those are not rare components. I mean, I'm simplifying a little bit, of course, here, but Unitree is successful because of the low cost, and its components are not exactly what you would call highly optimized mechatronic components. Even though they still like the motors are still combining quite a bit to make them perform the way they are. All right. So what I'm trying to say is that mechatronic approach is not somehow like the only approach that works, but it was an insight that people had back in the day, and that is how the discipline was created. The discipline was all about let's study how we can do all those things together and achieve synergy, right? But now importantly, you are not mechanical designers and you're not electrical designers. So for you, the design aspect might be a little bit alien because your specialization is in software, right? So for you, it would be like this kind of like introduction would sound like it leaves you astray. Now, what we will do is we will take one aspect of this large discipline, and that aspect is like, roughly speaking, what has to do with control and use of mechatronic modules. Like we will not spend time on, at least we're not going to spend much time on questions such as design, how to produce new mechatronic modules. This is far from your specialty. Instead, we're going to concentrate on understanding various mechatronic modules, especially motors. In fact, in your program, I think this is the course where you're going to understand motors. The electrical part of the motor, mechanical part of the motor, control part of the motor, model, sensors, everything. And motors is absolutely critical for robotics. Like it is a critical part of any robotic system. And deep understanding of motors is a requirement. Usually it is a requirement. There's not, not some strange, interesting knowledge. It is key. Often enough, maybe not absolutely everywhere, but very typical. So here you're going to check your background for one of the key aspects of robotics. So what I'm trying to say, I guess, is the course is necessary for you as a robotics specialist because we are going to cover one of the key background issues that you need to cover. Right. So that's the idea. The science itself, mechatronics, is important for various reasons, but for you, the course is important specifically for this aspect. Okay. Okay. Now, do we have questions about what I just said? If not, I will go straight into the first lecture. So the way I will structure the course overall is we will first think about electrical, like just electricity, electrodynamics, you can see. Then after that, we will see connection between this and what we call filters. We will be talking about circuits, filters, and in many ways we'll remember differential equations, Laplace, and so on. So not leaving electricity, we will explore those various fields, and all of this will be immediately relevant to control of motors. All right, after that, we'll quickly remember mechanics. There will be one lecture on mechanics, classical mechanics mostly, right? I mean, not more like completely classical mechanics, but basic aspects. And then from that, on the fourth lecture, we would have motors. We would spend 2 lectures on DC motor. We will discuss models. I will discuss performances. We will discuss various aspects that are specific to motors. Motors and are not, just electricity and mechanics. There is some things that are specific to the motors themselves. We will understand that, and after that, we will spend a little bit of time on control and so on. So the first half of the course is I outlined it. The first half, like the first 6 lectures. the reason I do it is partly to ask you not to be afraid. Today's lecture will be on electricity and electric dynamics. It is a school program. It is also, I think, part of your first year university program. So please don't be scared that it is too basic, or don't be scared that it is too, electrical and out of the left field. It's okay. The whole course is not going to be like that. So, okay, let's begin. So first, let us remember the very basics of the very basic, I guess, idea of electrodynamics. When I say electrodynamics, by the way, I'm talking about electricity in terms of currents and voltages, right? You can talk about electrostatics. So when you have a charge that produces electric field, right? Various interesting properties there. Here I'm talking about electrodynamics. So a current flowing through a wire, and the factors of life for this current would be resistance. There will be capacitors. There will be inductors, inducers, right? And then that is the electrodynamics. So something flowing like a current flowing through a wire. Okay. And one of the most basic aspects of this electrodynamics is what we call Ohm's law. Ohm's law. Okay. Ohm's law. And basically it tells you that the voltage across a resistor, right? So differential in potential across a resistor is equal to the product of the current that flows through the resistor and the resistance. Okay, that is the Ohm's law. If you know how much current flows through your wire, and there is a resistor, let's say, in the middle of this wire, what you can do is you can compute either like how much voltage is across the resistor, right? So how much voltage is being consumed by the resistor, if you want to speak about it this way. Or you can estimate how much resistance the resistor has if you know the voltage. So this ratio is just basically tells you that if you know two of those elements, you can find the third one quite easily. Okay. Just to quickly remind you, when we think about the resistor, let's say there is an input wire, output wire. By the way, it doesn't matter, right? The thing. When we say voltage across resistor, that means that you can measure voltage between those 2 points. Like if you had a voltmeter, you could measure at those 2 points, and that is where you would see this V. Okay, there will be a difference in potential across between those two. So that is what we call voltage. Current, I think, is quite clear. It's just the amount of charge that flows through this wire per unit of time. So that is the current. Resistance is then by definition the ratio of those two for this resistor. Okay. So the voltage across the conductor is equal to the current flowing through it times the conductor's resistance. Okay. Now, here, one of the useful ways to think about Ohm's law, that is to say, if we want to compute current, but we don't know it, we can always just, if we know, voltage, we can divide it by resistance and we will know current. What is typically happening is resistance is known. Okay, resistance is known. because if it is electrical component, you can just look up its resistance by the markings or in the data sheet. It will be known. Resistance is known typically, and establishing resistance is also not very difficult. So resistance is typically a known factor. Voltage is easy to measure. Like voltmeter is a easy, easy thing to use, and it is quite trivial to measure a voltage. Measuring current is not as easy, and instead we often don't measure it directly, but instead we use this approach where we measure voltage divided by resistance and get current. That is the way to estimate current. Okay. And in general, it is just important to know that Ohm's law can look like this too. If you have any questions about this, this whole thing, please interrupt me. Ask anytime during this lecture. I'll be happy to elaborate. I understand all of this is a repetition of something you learned from high school, so that's why I suspect you don't have questions yet, but please interrupt me as soon as you have. All right, now more complicated stuff. Previously, we were thinking about just one element, like a resistor or conductor, if you want, right? Now we're thinking about various conductors, resistors, etc., connected by wires. And now with that, we introduce what we call Kirchhoff's laws. Kirchhoff is famous for two laws that are used in electrodynamics in circuits. First is the current law. So the current law, Kirchhoff current law, says the amount of current that flows in and out of a node is equal to sum of it is equal to 0. So node is basically, you can think of it as just a point where you have wires connecting to it. Imagine you have 3 wires, you just kind of tie them together, and there will be a point where they all connect. This is a node. So the amount of current that flows in and out is the same. This would be quite obvious if you start thinking about electricity as water. Okay, that is a very famous analogy, and you might have heard it before. Current is the amount of charge per unit of time. Okay, amount of charge per unit of time. So the analogy with water would be like this. Water, like water itself, is charge. Okay, the amount of water per unit of time is flow. Okay, as you can imagine, if the water flows in and out of a junction, like you have pipes going in and out, let me just draw an example. Have a pipe going in, pipe going out, another going in, maybe another going in, maybe one other going out. Okay, they all pump water in and out of this junction. The junction itself doesn't have volume, right? It's just a place where they all connect. So it cannot store water. There's no place to store water. So the amount of water that comes in has to also come out. It is not possible for the water to be stored in the junction. So it makes sense that the amount of water that flows in, so equals to the amount of water that flows out per unit time. So that is what we would say, like the sum of flow of water in and out would be equal to 0. Same with electric charge. There is no place to store electric charge in the node. So the amount of electric charge that flows in equals to the amount of electric charge that flows out. That is all this equation tells you. Okay, all this equation tells you the amount of charge flowing in equals to the amount of charge flowing out, charge per unit of time is current. So the sum of currents that go in and out is equal to 0. We are denoting here current as having a plus sign if it goes in, as a minus sign if it goes out. That is the notational trick, you could say. All right? Clear about the Kirchhoff's current law?
Yes, clear.
Okay, good. Now, Kirchhoff has a second law. It's a voltage law. That one doesn't have at least to my taste, doesn't have a nice analogy like this. Of course, you can come up with a water analogy because, in fact, water systems and they have exact same laws as circuits, like Kirchhoff's laws are applied there too. But the analogy is not quite as obvious as with current law, so I'm not bringing it up here. But the voltage law, basically what it says is, if you have a closed loop circuit, closed loop meaning that you can like draw it like this, right? There might be branches going in and out, but there is also a circular loop somewhere, okay? So you can go in circle around this loop. Well, the idea is that the sum of voltages across all elements in this loop would be equal to 0. Okay. So you can say that the electrical potential, if we start from some point, it's going to drop, rise, and the sum will be equal to 0. Right. So we will measure electrical potential across, like voltage across this element, this element, this element, this element, and the sum of those voltages would be equal to 0. That is the idea. That's the idea. So that law, I think, is quite easy to remember. Quite easy to remember, and in a way, like one, I think, satisfying way to convince yourself that it must be true is imagine if you have like two lights connected to, let's say we begin even simpler. One light. You have one light connected to a battery, right? So here's your battery, here's your light, and there's that's all. Like you have a connection is shorted there, right? Okay, like this. It's kind of clear that the like it's not as logically clear as with the water example, but I think it's somehow intuitively it is easy to imagine that this bulb will drop just as much voltage as the battery produces. How we can show it? Well, let me just. I think with the drawing it is going to be painfully clear. So this is a bulb. I will draw it as a resistor. Resistors are sometimes drawn as those rectangles. And here's the battery. The battery is often drawn as a circle. Okay. And we'll connect them. Okay. How do I measure the voltage across the bulb? Well, let me measure it somewhere here, let's say, and somewhere here, let's say. I think at this point it is instantly clear that this is exactly the same as measuring the voltage across the source, across the battery, right? So of course the voltage across the lamp will be equal to the voltage across the battery. Just we can argue about the sign, but the voltage itself is the same. And it will be the same if we make like more resistors, like more lamps, right? It will be the same story. Like the sum of the voltage across them will be equal to what battery produces. And if we have two batteries, it will be the same, right? Like I can add a second battery here, nothing will change, and so on and so forth. So somehow I think thinking about it this way on the simple circuits makes it intuitively clear that the law makes sense. The law makes sense. Yeah, but you can also just memorize it. Like the first was the sum of all currents, second is the sum of all voltages. And yeah, I think it's not very difficult to keep it in mind. Right, that is two Kirchhoff laws. That is enough to do all that we have to do with circuits. So the laws are quite simple, and it is enough for us to work with circuits for this course. So that's quite nice. I know it's we're going to have a whole course where we're going to work with electronics, but we, circuits wise, those two laws are enough for us. So, it's pretty good. It's not very scary. There is a way to formulate those laws in this way. The algebraic sum of currents in a network of conductors meeting at point is 0. So that is the, like, in language, in the human language, we can write it the same. And the second law is directed sum of potential differences, so voltages, across any closed loop is 0. Right? So that is how they formulated using language. I'm not sure if this helps or not helps, but sometimes writing it in words helps to clarify, because currents in a network of conductors is maybe a little bit more clear than just I, more descriptive. So you can read this too if you have doubts later what this law is. Okay. Now finally, I'll engage you with something interesting. Before that, I'm almost completely certain you have already studied all of this before. So it was completely a recapture of what we had. Now, maybe I'm not sure. Maybe you still have studied it, but maybe it is new. I don't know. Let's see. So RL circuit, resistor inductor circuit. That is the simplest case, like simplest type of circuit, and the most primitive RL circuit looks like this. You can see resistor here. You can have an inductor here. Right? Here we can define like a voltage across resistor, voltage across inductor, voltage across battery, like this is a battery, like our power source, if you want. And this is our input, if you want. So this is the circuit. Okay, this is the circuit. Maybe I'll just for the interest, tell me if any of you already studied it. Please speak up.
Yes, we have this topic in our electronic course,
Great.
like in the second year.
Okay. So you had a specific course on electronics, right?
Yes.
So not physics 2, you mean, right? Not physics 2, electronics.
It's called physics 2.
Okay. So physics. So what classically would be electricity and magnetism. All right. Good. Great. So that's nice. Hopefully, maybe we'll make speedy progress, and if this still has been covered. Now, with the inductor, I think the like a scary way to approach it, the way that I'm not going to use, is to start thinking about it as a coil, coil of wire, where according to laws of electrodynamics, you have magnetic flux have electrical and magnetic fields interacting and so on. Complicated stuff happens. This I would like to avoid. This is, I understand, is tempting to think about it this way because it is a physical object where indeed you have a coil, right? So you kind of want to think about it this way. But instead, what I propose is to think about this circuit as a differential equation. So differential equation that describes the circuit is this. Well, let me go step by step. So this part of differential equation, L times di dt, is what describes the voltage across the inductor. So the voltage across the inductor is L, where L is inductance. Okay, L is inductance. Just a coefficient of the inductor, like it has to do with the physical dimensions, number of coils, and so on and so forth. By physical dimensions, I mean mostly number of coils. Anyway, so you have this this part that describes the behavior of inductor. This part describes the voltage across the resistor. Notice here you see familiar expression I times R. So this comes from the Ohm's law. So if you remember, Ohm's law tells you that voltage across the resistor, or if you want, conductor, is equal to current flowing through it times the resistance. So that's it. That's Ohm's law. Okay. So R here is the resistance. And finally, here, V is input, some kind of input. You can think about it as a battery, but battery is not very good analogy because battery usually produces constant input. And we're not going to think about constant inputs usually. Input can change with time. So you can think about it as input, as a driving voltage, as something you basically input to the system. Okay, but a battery, if you like it, if it helps you think about it this way, you can think about it as battery. But we can change it. If you have done some work in the lab, you have seen those laboratory sources of power sources, right? Where you have a knob, you can turn it, and you can produce different voltage on the as the output of this power source. You can think of V in as this power source if you want. So like it works like a battery, but we can expect changes in the voltage if we want. So it doesn't have to be static. All right, and that is it. That is a description of this circuit. Why is it correct? Like, where did it come? Where did this differential equation come from? Like, it looks completely random, right? Why should it look like this? Well, it is because we use Kirchhoff's law. We use Kirchhoff's law. How do we use Kirchhoff's law here? Well, we say that here is a closed loop circuit, and the sum of voltages on this loop should be equal to 0. So the voltage or the difference in electrical potential across this inductor plus voltage across this resistor plus voltage of this battery would have to be equal to 0. If we assume that the battery produces positive voltage changes and everyone else produces negative voltage changes, which has to do with the fact that they consume power and battery produces power, then we can put battery on the right-hand side, everything else on the left-hand side, and we get this equation. So this is basically just a second Kirchhoff's law. That's what we did here. We used second Kirchhoff's law. Okay. It's going to be more or less like a basic for a second Kirchhoff law. Right, that's it. So you can see how we got this equation. Now, what is it useful for? What is it useful for? When I show you this, what do you call it? This circuit. what can I ask of you, right? Like, let's say I'm asking you to please understand it, please describe it, please solve some problem for me. What kind of problem can I ask you to solve using this circuit? If you had like any, okay, not try to remember the problems that you were solving like a year ago. It might take a while. But let's say I ask you this question: how fast, if we give here like input of, let's say, 10 volts, like the battery produces 10 volts constantly, what would be the final current, like after, a lot of time passed? Like, let's say as time goes to infinity, what would be the current in this circuit? Well, this we can find by solving this differential equation. We'll just put 10 here, solve differential equation, and the solution will tend towards a certain number, right? It will tend towards a certain number. So in this sense, this differential equation answers what we want to know, right? Another answer, another question. Let's say what I want to ask is, if we measure this guy here, okay, we measure voltage across the inductor, and we put again 10 volts in here, constant 10 volts. What would this reading tend to? Okay, that's another question to ask. And we can also find it by solving this equation first, and then looking at this term specifically, like this blue term. We can look at, like we can substitute the solution back into the differential equation, differentiate it, multiply it by L. Also, not substitute, we can just like, we get I, differentiate I, multiply it by L, etc. There are easier ways to do it, of course, there are easier ways to do it. But yeah, like if you know I, we could always just take V minus IR, and we get this term. So there are ways to do all of this. But basically what I'm trying to say is, almost anything you can ask about the circuit, I can answer solving this equation. Because this equation describes how current behaves given voltage as input. So this equation describes the behavior of the circuit. So this is sufficient in some sense. Like, it is not sufficient in like any possible sense, every possible sense, but it is sufficient in some sense. So we could use this differential equation to describe the circuit, to solve actual problems, right? Do you have questions so far?
No, I don't have.
But in your electronic course, did you study this equation?
Yes, we studied it.
Oh, so you saw the differential equations of the circuit.
Yes, of course. Yes.
Great. Very good. Very good. All right. Then let us proceed to the next one. So here, before we go on to the next circuit, so I just want to emphasize there are a few ways to look at this, circuit. So first, this is of course Kirchhoff's voltage law. Okay, Kirchhoff's voltage law. This voltage across resistor, as I said, right? This is voltage across inductor. And since it is a differential equation, it also acts as what we call a filter. We're going to discuss it a whole lot next lecture, filters. But yeah, it acts as a filter since it has dynamics. In the simplest way, you could say, no matter how fast the voltage changes, the current is not going to change instantaneously after it, right? So you could say that somehow input voltage does not instantly changes the current, right? So this already kind of looks as like basically there is an inertia in this equation. So you could use it to filter out, for example, high frequencies, right? We'll discuss all of this later. Okay, all right. Now, RC circuit, resistor capacitor circuit. That is alternative form of a circuit. And in its simplest case, it will just contain a resistor and a capacitor, right? Resistor and a capacitor. So there are two ways to draw it, like one with a battery, one without a battery. Like this is without a battery. The left-hand side is with a battery, okay, with a battery. Okay. Now I will describe you the short circuit case, okay, short circuit case. So the one on the left, and we can describe it in this way. The capacitance times the rate of change of voltage, rate of change of voltage. So this has to do with capacitor. Plus here the voltage divided by resistance. This has to do with the resistor. Their sum is equal to 0. The sum is equal to 0. I think we can kind of recognize that, well, first of all, the form of this equation is very similar to the form of the equation that we saw previously. So what we saw previously was the differential equation with respect to current. This is a more rare differential equation. It is a differential equation with respect to voltage. We're not going to see it very often. I just wanted to show it to you so you kind of like see it once at least, right? People actually use RC circuits often where the input is current, not voltage. This has to do with various possibilities you can have when you design electrical circuits, etc. Sometimes it is easier to produce voltage as input. Sometimes it is easier to produce current as input. Voltage is more typical. So voltage is what we often have. But sometimes you can produce input current as input. Okay. Sometimes. And the form of differential equation is exactly the same. So you can expect the behavior of two differential equations will be exactly the same as long as you remember that the first one deals with current, second one deals with voltage. All right. So you can see that different beasts behave exactly the same way, but the quantities that we measure are different. All right. How did we get this equation? I'm not going to derive it for you here. We're not going to use it like this one. We're not going to use in the course. So I don't want to spend too much time on it. But basically, you can see that this is current, right? If you remember Ohm's law, like V equals to R times I, right? So this is current. And together, this looks like a Kirchhoff's current law, right? So you can imagine if you put a node here, maybe you that's like how you organize this equation. You can say that what flows in equals to what flows out, and so on and so forth. Right? So this is somehow related to that. And of course, here you can also break V as Ri, and then you would have R does not change with time, so R will go out of the derivative. You will have C times I change, like rate of change of I times R. and so on. So this equation this equation we can derive using first like Kirchhoff's current law, and that's like one example of how we can do it. Now there is like you could say that this is like elementary behavior, or like this part describes elementary behavior of the capacitor, in exactly like previously we like L times di dt described elementary behavior of a inductor, right? And Ohm's law describes elementary behavior of a resistor. Right? Indeed, this is true, and this is a typical approach. We could say, okay, we have an element of some kind and it has a certain behavior. And we just put it in the equation and we use it. Like we don't spend too much time asking why this behavior is produced. This is the other chapter of electrodynamics, but we use it directly. We know what behavior to expect and we use it, right? So this is like in a way the approach that we'll take, but not remember that it is possible to reason about where this behavior comes from, what the behavior is, and so on and so forth. So it's like it's not a mystery why we have those parts of the equation. Like how you can just ask internet, I guess. For example, how to compute voltage across the inductor and why it is proportional to the rate of change of current, and you'll find out, from the position of more basic notions of electrodynamics, right? So it is not a mystery, like you can study it. It's just that here, for simplicity, we avoid discussing it. But what we are interested in specifically is this type of connections where we notice similarity. Like this differential equation, we don't need to study it separately from the previous one because they look exactly the same. So as long as we understand one, we understand another one automatically, but we need to remember the change of variables. All right, good. Now, the maybe more ambitious type of circuit is RLC circuit, where you have resistor, inductor, and capacitor, all three, right? Resistor, capacitor, inductor, and here is a power source. And here I write the differential. I will write a model. Okay, it will be written as a differential integral equation. And apologize for maybe introducing it all of a sudden. Here is a part that you are familiar with, right? This is, let me use as a type like this. This is what you're familiar with. This L times di dt. So we're familiar from the previous equation. This is the voltage across this again voltages. So we are talking about Kirchhoff's voltage law. So this is the voltage across this inductor, right? This now is the voltage across this resistor. And finally this part with this part together is kind of interesting, is the voltage across this capacitor. The voltage across this capacitor. And together they equal to what the battery produces. So together they equal to what the battery produces. Here's the battery, here what the battery produces. So I think like the connections are clear, like where we get those terms is clear. Maybe the one unclear part is this expression here, right? Well, on the next lecture we will see more of it, so it will become more familiar. But you can clearly recognize here that some integration was taking place. Like here you can see Like this constant clearly looks like it had something to do with integration and so on and so forth. Let's look at it a little bit. So this guy is a rate of change of charge, right? Rate of change of charge. So how much charge flows through this wire. Since it is a single circuit, the amount of charge flowing in each particular direction is exactly the same, right? Like the amount of charge flowing here is the same as charge flowing here, same as here, same as here. Like all this charge is the same because you can say, I can argue it in various ways. I can say because of the Kirchhoff's current law, or I can say, you know, if you think of charge as water, like it is impossible that through this cross section there's one number of amount of water flowing, and through the next cross section different amount of water is flowing. Like where does the water come from, or where does the water go? Like it has to be the same. So the amount of charge that goes around here is exactly the same in each cross section. So this charge, this is the rate of charge, rate of charge per unit of time that goes in particular through the capacitor. Okay. Now we integrate this. So we you can say we integrate how much charge approaches, let's say, this plate of capacitor per unit of time. We integrate it. So but what we get as a result is charge that accumulated on this plate, charge that accumulated on this plate over the entire time that we are simulating. Okay, so the charge that accumulated on this plate over the entire time. Now, if we divide this charge by the capacitance, what we get is exactly the voltage across this capacitor. Okay, except capacitor might have had charge before, so it didn't have to start with zero charge. It could have had charge before. And if it had charge before, we can model it as this V0. So we can say that initial charge divided by capacitance is V0. That's it. That's what V0 is. It's basically the initial conditions for the capacitor. Capacitor could have been charged in the point time T0, or it could have been discharged. We don't know. So that's why we have this element here. Initial conditions, you could say. All right. So I think this is quite clear. Now with this expression, you could see how the RC circuit would have looked like. If we get rid of this guy here, if we get rid of this guy, we would have had the RC circuit. So the RC circuit would have looked like IR plus this initial charge, whatever it is, plus the integral. So it would have become an integral equation. What I showed you previously was a differential equation describing RC circuit. This is an integral equation describing the same circuit. Okay. Okay. Any questions about this? Okay. This, I think, let me check. What else? Yeah, okay. So this is it for the circuit. This is it for the circuits. Next lecture, we'll spend the whole lecture understanding the implications of the circuits when we are thinking about filters. So, you know, this lecture was just basics. We understood that circuits exist and can be described by differential equations. Next lecture will be filters. Now, we need just a couple more notions before we can call it quits. So we still have time, right? Sorry, I didn't have time in front of me. We have just a little bit of time. Okay. We have just a few slides more. So first, there is something called Lorentz force. Lorentz force is a force that acts on straight wire, or on any wire, but in particular on straight wire, where there is a current flowing through it, and it is placed in magnetic field. Okay, it is a interesting electrical phenomena. Okay, it is an interesting electrical phenomena. Now, how do we compute Lorentz force? Well, it is equal to the current that flows through the wire. That is a scalar quantity. Okay, scalar quantity. So like 5 amperes, 10 amperes, and so on, times the cross product of V, W. W is the vector whose length equal to the length of the wire, and the direction is equal to the direction of the current. Okay, so the current is by definition it goes along the wire, right? So we can measure in which direction it goes. And so this vector would be length equal to the length of the wire, direction equal to the direction of the current. And cross product of this omega with B. B is the magnetic field. Okay, so we have magnetic field is a vector, and we have this. We're assuming that it is uniform. Magnetic field is uniform, not like pointing in various places, because then the formula will become more complicated. It is possible. It's possible to describe all of this in a more general form. This is just a very simple form where you have a uniform magnetic field. It points in one way. You have a wire with a current. It points another way. And to compute Lorentz force, you find cross product between the direction of the wire and the current, right? And the magnetic field, you find cross product and multiply it by the current. That's it. That's the Lorentz force. Yep. So it is a physical force that would move this wire. This is important because this force is essentially, you can say, what moves DC motor around. Like DC motor, when it rotates because Lorentz force forces it to, like its wiring to displace. Right. So that's why we need to remember it. We would use it on the lecture on DC motors. Okay. Another one is electric power. We need to remember what electric power is. So electric power is the rate of doing work. Like any power is the rate of doing work. Okay. So work is energy. Work is measured in joules. It is always energy. It like a scalar quantity. And power is also scalar because it is the rate of doing work, the rate of change of energy. Okay, so it will be joules per second. Now, in the case of a resistor, the power associated with the, its work as a resistor, as it conducts current through it can be written this way. So this R times I squared. Okay, so this is the electrical power for a resistor. This we'll demystify it in just a moment, but yeah, this is how we compute electrical power for a resistor. Now we can write the same exact formula in this way, where we say it is voltage times current. Voltage times current is power. This should be somehow feel good, this kind of thing, because it should remind you of mechanical power, where mechanical power is force times velocity, or torque times angular velocity, right? Yeah, so like force is famously what produces change of velocity, right? And here voltage is what produces change of current, like especially in, let's say, RL circuit. And we have this same relation with power. So there's connections with mechanics, but we'll see it on the lecture mechanics. Okay. Now, this is how we compute electrical power. Now, the power of heating, that is a specific power, generated by a conductor. So conductor and resistor in this case are synonymous. Can be computed like this. It is equal to for some reason I couldn't click. Okay. It is R times I squared. So it is again resistance times current squared. And this is basically the power, so the amount of joules per second that goes into heating. So you can say that's the rate of change of energy that was transformed into heat. Okay. And since energy is like unit, the same unit in like thermodynamics, in classical mechanics, in the electrodynamics, you could use this information to say, oh, how much more temperature would a resistor gain or the environment gain if we transfer this much power into heat. And you will be able to do it because if you know how many joules per second are being transferred to heat, you could compute the change in temperature if you know like other thermodynamical parameters. So it is useful. But especially it is useful because you understand now what we mean by the power of a resistor. The power of a resistor, so this guy here, is essentially the same as power of heating. So it is a resistor the only work that it does, it transfers electrical power, like electricity, into heat. Okay, so it dissipates heat. Each time you conduct a current through a resistor diminishes this available, you can say, available power by this amount. So just basically transfers electricity into heat. And it is important to keep in mind because it will be useful later when we talk about efficiency. Right. So that is what resistors do in terms of power. All right. Now, if you want some more information about this, like just to refresh using something else other than the slides, here's a recommendation, chapter 7 from Stanford. It is mostly about circuits, and it would cover material from the next lecture too. So I don't recommend you like reading the whole thing at once, but you can, up to you. Like later when you try to study, you could definitely reference it, but you could do it now as well, completely up to you. Right. Now, as usual, the slides are available on this GitHub page. So you can now, if you want to scan the QR code, and you would see the page, so you don't have to type it. Or I will send it in the group. The slides for the first, I believe, 6 lectures are already there. I would try to update slides well ahead. But yeah, you'll be able to use slides to prepare for the exams, for the labs, for anything. The slides are meant as being, being a little bit like lecture notes. You notice I write everything out on the slides. So make sure you use them in preparation. You also notice now the pace is relatively slow. We spent time on basic things, and we can afford it. Like the content of the course will afford us this kind of pace. But we will go into details. Like pretty much everything that we discussed today will be used in the next lectures. So while the pace is slow, like in terms of how many new things we introduce, it is there will be demand. Like next lecture, I already would expect you to remember what we said about Kirchhoff laws, other things like that. And in lecture number 4, we will have to remember the first two lectures in the entirety. Lecture number 5 we would use the power, like the definition of power, and so on and so forth. Like there will be a lot of this kind of like going back and forth. So you know, I hope you will bear with me, even though the pace is slow. It may be not exciting at first. Hopefully, next lecture will be more exciting, more challenging, let's say. But I would still want you to try to pay attention, refresh whatever you forgot, so that we could get the maximum out of the next lectures. My aim is at the end of the course for you to have a complete mastery over what pertains to mechatronics and motor control, every aspect of motor control, from you could say design to actual like writing down control. So I would want you to try to pay attention to even those boring things that are partially covered by other courses. Like next lecture, you would see some of what you knew from control theory, for example. Right? Still, please pay attention because the outcomes will be worth it. Right? Thank you so much for your attention. I will stop the recording here, and we can have a Q&A about points and everything else. Let me stop the recording.